Hi everyone. Okay, so welcome to our next lesson on advanced calculus. And today we are going to look at the concept of curvature, which is also associated with the space curves that we have been dealing with so far. You see, so in this section, we'll try to get an idea of how to quantize curvature and then see how we can then work it out um, using the tools that we have already developed for space curve, you see. So to get a brief idea of what do we mean by exactly by curvature, let's just look at the space curve in 2 dimension. So suppose we have a following space curve in 2 dimension, which is being traced maybe by a moving object like that, you see. So if maybe it's a particle that is moving in this direction that is tracing out the curve, we can see that there are some regions of interest that we can focus on at this instant. And these regions of interest that you can focus on at this instant, one of which is this one that we have here, and this one that we have here, and this one that we have also there, and many other regions that we also have that side, you see. So these regions, we can see that one thing that characterizes them is that there is always some change of direction that happens there, or in some way we can say that there is some sort of bending that is happening as this particle is moving. You see that? So if you are to study this locus of this particle, you will see that as it moves, it is busy taking up different turns, you see, changing its direction to face another direction at certain speed. So what we want now is to see if we can be able to measure all these things that we can refer to as curvature. So curvature is a term that is used mostly to quantize the degree of bending of a space curve. You see that. Remember, we really encounter space curves that are actually straight lines in most cases. All space curves that we deal with, they are curved in some way. They are not just simple straight lines. You see that. So what we want now is to have the ability to work out the degree of bending that lies within a certain section of a space curve. You see that? Like if you are to travel maybe from this point to that point, what can you say about the degree of bending for that space curve in your journey throughout that motion? And also, what can you say if you travel from this point to that point, what can you say about the bending that you encountered in that region? You see, so we can see just by looking that the bendings that we have in all these sections, they are of different degrees. Some of these parts are much more bent than the other, while some of them they are less bent. So it is the degree of bending that we actually refer to as curvature, you see, when it comes to the language of space curve. So today we want to see actually how can one be able to quantize this degree of bending of a space curve using some mathematical tools that we have today, you see. So to put some notes down, so curvature can be defined as a measure of the degree of bending of a space curve. You see that, just like as we have stated. And this quantity is usually denoted by kappa of t. because as you have seen, bending is something that changes it in terms of the parameter type. You see that. So if you are to look at some instances, the curve will be bent much more slightly than other regions where the bend is of higher degree. So this quantity that measures curvature is denoted by the Greek letter kappa with respect to time. You see, and this quantity is given by, so if you want to measure it, kappa of t is just the measure of the rate at which the tangent vector is changing with respect to the arc length. You see that? So if one way we can use to actually quantize the curvature of a curve is just by tracing out how the tangent vector is changing with respect to arc length. You see, so if we can measure out how that vector is changing, it's a direction with respect to arc length, it can give us a way of actually measuring this thing that is called the curvature. You see that? But now, if we were to look closely and using our chain rule, so if we were to play around with some chain rule, we can see that this quantity kappa of t, which we have already defined as the change in the arc length with respect to the change of the tangent vector with respect to the arc length, can be written as the change in arc length with respect to the parameter t times the change of t with respect to the arc length, like that. You see, so if you look at the first expression, you will see that the first expression inside this absolute function, it's just a measure of the change in the unit tangent vector with respect to the parameter t. So it's just t prime of t. Whilst the other quantity that side, if you can look, this is simply the reciprocal of the change of the position vector with respect to the parameter t. So if you still recall, we encountered this when we're doing the arc length parametrization. So from the arc length parametrization, we witnessed that we have this result most of the time, that the change with respect to the parameter t is just simply ds dt. So this is what we just used here to provide some simplification, and we can now simply see that this thing that is called the curvature with respect to time is simple the measure of the change of the unit tangent vector with respect to time over the measure of the position of the change of the position vector with respect to time, like that. So this is one nice way of actually working out this quantity that is known as curvature. So every time when you want to work out the curvature, this is one of the formulas that we can use, you see. But though this is actually the correct formula that can be used to measure this quantity, it is not the one that is used much more frequently. There is another suitable formula that can be used to calculate curvature, which can be derived actually from this one, but we won't go along with the derivation of that formula, but we're just going to state it and see how it can be used to do some calculation, you see. So it can be shown also with some bit of mathematical arguments that the curvature is also given by, so this thing that we refer to as the curvature, it can also be given by the simple formula K prime, which is the cross product of R prime T with R double prime T over R prime T cubed, like that. So this is actually the best way to evaluate curvature. You see that? Because why would one actually prefer to use this result more than the one that we have just stated before? It is because this one is time consuming. It needs first the evaluation of the unit tangent vector, and then we can go all the way to also differentiate to get R prime of T and then simplify. But this one, it sticks to using only the position vector for calculation, and we can see that we just need to find the first and second derivative and then take the cross. So this can be an easy task to do than to do that one, especially when the problems become a bit much more intense. You will see that it is always much more preferable to work with this version of curvature than the first version of determining curvature. So what we are going to see now is we are going to look at examples where we can demonstrate how exactly can one calculate curvature from this formula that we have stated. You see, so you can note the formula down, as I won't be scrolling back and forth to just check the formula. So it's good to always keep these formulas into your memory so that every time when you need them, you can just recall them and use them. So which is what I'm going to be doing currently. Okay, so now what we're going to look at, the following example. And in this example, what we have is we are given the following problem. So they are saying determine the curvature of the curve RT equals to t squared t cubed at the point 1, 1, 1. You see, so this is the question that we are asked. We are asked to find the curvature at this point. You see, so we want to see now how far this object has turned when it reaches that point. That's what we are interested in right now. So let's see how to work this one out. So to work this one out, we are going to first recall the formula that we are going to need to evaluate curvature. So remember, curvature is given by, so this thing that we call curvature, which is K prime of T, it is given by the absolute value of F prime of T crossed with F R prime double T over absolute of R prime T all cubed. So which means we see that we have to take the position vector and differentiate it 2 times to work out the curvature. So now what is R prime of T in this problem? So we see that R prime of T, we differentiate each component with respect to T, and we get 1, 2T, 3T squared, like that. Then again, if we differentiate that, what we get, so we get what we get 0 here, then we get 2 here, then we get 6T. That's what we obtain at this instant. But now we are asked to find the curvature at this point. So if you are to look the point that is given, you can see that the general point has the x component as being t, and the point given has the same x component as being 1, which simply shows us that this particular point that is being referred to here, it corresponds to a parameter value of 1. So which means in some way we are interested in finding the curvature when t is equals to 1. So which means now I have to take these two and evaluate them when the parameter is equal to 1. You see, so what do we get? So again, we can see that r prime of 1 is equal to 1, 2, 3, and r double prime of 1 is equal to 0, 2, 6. So this is what we have. So what does that imply then? So it implies now the cross of r prime of 1 crossed with r double prime of 1 is equal to what? So we know that the cross is defined as just this using metric notation. It is the evaluation of this determinant where the second row is taken by r prime, which is 1, 2, 3, and the last is given by r double prime, which is equal to that. So let's simplify and see what we get now. So we know already how to evaluate the determinant of 3 by 3 matrices. So to find the determinant of 3 by 3 matrices, we now know the logic. So I'm gonna just work it out on my head. So we have 12 separating 6, which gives us 6i. And then for j, we have 6 minus 0, so we get minus 6j. And then for k, we have 2 minus, then is plus 2k, like that. So which shows us that the cross between r prime at 1 and r double prime at 1 is equal to that. But when we look at the formula, it requires actually the absolute or the modulus of this. So now what is the modulus of what we've just calculated? It is just as follows. It is just the root of 6 squared plus 6 squared plus 2 squared, which is equivalent to what? So it's more like saying 36 plus 36, then plus 4, which gives us 76. So we get this as root of 76, like that. Then, if you look again, we need also to know the absolute value of r prime of 1 again. So what is the absolute value of r prime of 1? So the absolute value of r prime of 1 is, so we see r is just 1, 2, 3, so it's going to be root of 1 squared, 2 squared, 3 squared, which gives us what? So 3 squared is 9 plus 4, 18, and then plus 1, which gives us 14, like that. So therefore, the curvature that we are looking for at 1 is going to be root of 76 over root of 14. So what do we get now when we take this and simplify it? So if you are to simplify it, you will see that you will just get the root of 38 over 7. So we get the curvature at that point as just 38 over 7. So yeah, this is how we get to work out the curvature of any given curve. You see, so this formula serves to be the best one in the evaluation of curvatures. So now let's look at another different example again, because you know, one example is always not sufficient to get exactly what's going on. So let's look at another different problem, which is a bit tougher or trickier than the previous one. So what we're given now is determine the curvature of the curve r prime of t, which is equal to t minus sine t, 1 minus cos t, and t at the point root pi over 2 minus 1, 1 pi over 2, like that. So now we want to find the curvature of this curve at that particular point. You see, so remember, every time if a point is given, every point must always be associated or must always correspond to a particular parameter value, which when you plug it into the position vector, you always get that point out. And to see that, it's always done by inspection. So by inspection already, we can see now that if you compare this and that, you can see that this point, to get this coordinate here, you can establish t to be power over 2 and you get it done. So which means you can see that this point corresponds to a parameter value of pi over 2. So it means this point, to obtain it, you just have to plug in t to be pi over 2, then you can get it done. You see. So now what we want now is to find the curvature of this curve at this particular point. So now we have to differentiate our things. So now how do we solve? So now what is r prime of t? So we see r prime of t is just 1 minus cos t, and we have sine t, and we have 1, like that. So the other thing that we can do now, you can differentiate again to get the second derivative, which also is going to be a sine t cos t 0, like that. So now what we can do now is to evaluate all these two at the parameter value given. So now I have to find what is r prime at that parameter value of pi over 2. So I have to put now this. So when you put cos pi over 2, you get 0, so you just get 1 as your result. And when you put sin pi over 2, you get 1, so you get 1 on 1. And what about r double prime of pi over 2? So you put sin pi over 2, you get 1, and here you get 0, you get 0 there. So this is what we have. So now we just have to find the cross of these two, because we now know the formula requires the cross of these. So this implies the cross of this vector and r double prime at pi over 2 is equal to what? So it's equal to ij k and 1 1 1 1 0 0. So which gives us what? So again, dealing with this, we can see that when I close I got 0 in I, because I have 1 0 that. Then I close in j, I have 0 negative j, so I just get j. Then for k, I close for k, I have minus k as my final solution. So this is what I obtain for my thing. So the next thing now, I have to find the absolute value of these two, which is the modulus or the magnitude of this vector. Remember, a cross always produces a vector, so we want to find now what is the magnitude. So the magnitude simply here is 1 squared plus 1 squared, which is simple root 2. So we can see now that this is just equivalent to root 2. So now the other thing that we need also as well is as follows. So we need to evaluate r prime at pi over 2, the magnitude of this alone, which is going to be root of what? So I've just realized something that I forgot in the previous question, which I'm going to correct here. So here, if we check this vector, we see already that this was 1 1 1. So the absolute is 1 plus 1 squared plus 1 squared, which is simple root 3. You see. So now, what do we know? So we know that what we call the curvature of t is simply given by r prime pi over 2 crossed with r double prime of pi over 2 over the r prime of pi over 2 all cubed. So I forgot the cubed in the previous problem, which is what I'm going to fix after this. So therefore, what is k of t here? So we see that at the top already we have root 2. So we put root 2. And at the bottom we have root 3 all to the power 3. But what is root 3 all to the power 3? This will give us root 2 over root 3 means, so this part, it simply means root 3 root 3, but we know that these two give us just 3, so we have 3 root 3 at the bottom there. So we just have 3 root 3. So if you want, you can still rationalize, and you can get k pi of pi over 2, because t here is already pi over 2 that has been established. So it means the final solution, when you rationalize, whereby you multiply, you just get root 6 over, because I multiply by root 3 both top and bottom, and I'll get root 3 over 9. So this finishes our problem. So yeah, this is how we work out the curvature. But yeah, before I forget, for the previous problem which we did, this was supposed to be a cubed here. So what was supposed to happen is there was supposed to be a cubed here, which was supposed to give us something like outside as 1 over 14 and that. So yeah, those are things that I forgot. So it was supposed to be that cubed, and then this then will give us this result that we have here. So yeah, this is how you actually work out the curvature of any given space curve at a particular point. You just have to use this formula, calculate everything that you need, find the cross, and then do your substitutions, and then you get the curvature out. Otherwise, that's the end of this lesson. Thank you guys for watching. See you on our next lesson.